Good morning, good afternoon, good evening, and thank you all for joining us today for the Snack and Lark webinar on the case for steel road bridges with a low carbon footprint. Before we start, a couple of housekeeping rules. First of all, can you please, throughout the presentation, put your question in the question box, and at the end of the presentation in the handout, you will get a copy of the PDF and anything else related to the presentation. So today we'll be talking about this topic, which is part of a series that Lowri and I have been working on for a while now. We first published an article at the British Bridges Design and Engineering magazine, which again a link will be given, talking about all this. And this is today our first presentation focusing on the life cycle assessment. And then yeah, it's going to be a pretty exciting one. So, Lowri, can you please talk about yourself?
Yeah. Morning, evening, everybody. I'm Lowri Swygart, a bridge engineer who specialises in decarbonisation of civil infrastructure based in the Queenstown office in New Zealand. I'm originally from the UK, where I also worked for WSP as a bridge engineer and helped develop the strategy in the early stages of the civil bridge and engineering discipline, which would reaching WSP's ambitious decarbonisation target of halving carbon emissions in design and advice by 2030. Raed, introduce yourself.
Yeah, that's a good intro. Raed Sarraf. Hopefully some of you have seen me before by now. I'm Technical Principal Asset Integrity Management based in Christchurch, South Island of New Zealand. So both of us are from the South Island. And a lot of my expertise over the years have been related to the different stages of a bridge, from its design, refurbishment, maintenance to the end of life. So I have a pretty, I guess, a unique perspective of each stage of a bridge life, all which is also, again, useful when we want to deal with decarbonization. But anyway, enough about me. Now it's all about Lowri, and away you go.
So the purpose of this presentation is to evaluate the carbon benefits achieved from combining traditional construction materials with low carbon alternatives. So we'll be asking two questions. What scale of carbon reductions can we actually achieve through this approach? And are the current standards and guidance actually leading us to make the most effective decisions? So why do we need to move on from traditional construction materials? The construction and operation of the built environment make up 40% of global greenhouse gas emissions. And as many of us know, two of the most used and most carbon intensive materials are steel and concrete. And significant work is being undertaken to decarbonize these. And these innovations will be critical for many countries who are trying to reach 2050 net zero targets. However, it's anticipated that a large scale of low carbon steel and concrete solutions won't be widely available in the industry by 2030. So what are the current opportunities to enable us to decarbonize? Here we can see the global warming potential of steel, concrete and timber. And in this case, it's pine glulam, which is commonly used in New Zealand. So we can see that steel has the highest global warming potential, followed by concrete and then glulam, once you've taken into consideration the biogenic carbon storage, which is sequestered during the growth of the tree. So timber presents itself to be a superior option for supporting low carbon design in comparison to steel and concrete. However, engineers are well aware of its strength and durability challenges. And there is a lot of question across the industry of how the sequestered carbon is actually considered. And one of the key questions we wanted to understand was what scale of carbon reductions can we achieve from combining traditional construction materials such as steel with low carbon alternatives such as timber. So we're evaluating a new proposed system, a steel and concrete composite timber hybrid, or CTH for short, where we have replaced steel cross girders with glulam cross girders within a conventional steel concrete ladder deck system. And we've designed the solution with one of our senior bridge engineers here in New Zealand. So we've carried out a whole of life cycle analysis of both the conventional steel solution and the CTH solution. So this bridge was 57 meters in length with 2 spans and a width of 12.5 meters. And the all steel solution is assumed to have cross girders at 3.8 meter centers, whereas the scenario with the glulam scenario is at 1 0.8 meter centers with a bigger cross-sectional area to account for the difference of structural properties in comparison to steel. So the idea of this solution is that we can take advantage of the structural properties of steel while utilizing the low carbon benefits that we can achieve through timber. So before we delve into this study, just a reminder that the findings within this presentation are theoretical only, and they've been carried out as a thought piece. So we've carried out the life cycle analysis, and it's a simplistic and comparative study that has been undertaken. So only the materials within the superstructure are considered. Furthermore, the study only considers the data which is actually presented in the environmental product declarations, the EPDs, and this accounts for module A1 to A3, B4, C3 and 4, and module D. And in all cases, the bridge's service life is assumed to be 100 years, with a harvesting rate of timber of 25 years. And the calculation principles that have been used are the I-Shukti, how to calculate embodied carbon, and also their paper, timber and carbon sequestration. So just to make sure everybody is up to speed, how do we actually calculate carbon within civil infrastructure projects? So a whole of life cycle analysis is made up of all the activities across the project life cycle which will cause carbon to be released into the atmosphere. So we have three main stages: the before use stage, which is cradle to gate, the use stage, and the end of life stage, which is cradle to grave. And then we've also got the cradle to cradle, which is the inclusion from module A to module D, which is benefits beyond the system boundary. So this accounts for material circularity, like the recyclability of a material. So it's really important that when we do a carbon assessment that we have a look from modules A to D to ensure that we've got a true representation of the whole of life carbon. So one way of representing a whole of life carbon analysis is in a cumulative carbon profile. So to understand how the carbon builds up over time over the service life of that infrastructure asset. So as a quick example of how they work, we've got years on the x-axis, and then we've got the carbon release on the y-axis. So if we are building a bridge, we'll have module A1 to A3, which is the raw material, the supply, the transport of that raw material to a manufacturing site, and the manufacturing process. We'll then have A4, which is the transportation of that material to the construction site. And then we've got construction site related emissions. And then we might have maintenance emissions, so repainting and repairs and things like that that happen over the service life of the asset. Following this, we've got end of life service emissions. So this is at the 100-year mark that we've assumed that the infrastructure will last for. Whether the infrastructure is demolished or replaced, this is what is accounted for in module C. Following this comes module D. So this is where we have the benefits and load beyond the system boundary, and this accounts for material circularity. So this, what we've got on the screen now, is a typical cumulative carbon profile of steel, where we might have a high module D. And a carbon profile like this really helps the understanding of how the carbon is building up over the time of the infrastructure asset and how it can actually reduce with that module D as well, and hence showcasing why a cradle to cradle assessment is really important to take into consideration. So it's slightly different when we're thinking about the cumulative carbon profile for timber. So because we get that biogenic carbon storage when the tree is growing, which is highlighted in green. So this is for typical glulam, where we've got minus 804 kilograms of CO2 equivalent. So this is often thought of as negative carbon. However, the rules in the I-Shukti outline that all carbon accounting must start from zero, and you can only account for that carbon once the harvesting period of the tree, which we've assumed to be 25 years, has been achieved. So additionally, depending on what end of life scenarios you assume, which is in module C highlighted in red, all of the biogenic carbon can be assumed to be released back into the atmosphere, or it can be stored. And we'll touch on these reasons later on. So for an example of how this looks in a cumulative carbon profile, we'll still have the same A1 to A5 structure as before. And then once it's built, we'll have this 25 years where you can then start claiming that biogenic carbon storage. And then we might have the maintenance emissions, and then you'll have module C, end of life emissions, as well, which will also depend on the assumptions that you've made at the end of life. So for example, if you're burning it for energy recovery, obviously this carbon that you've saved here is then going to get released back into the atmosphere. So you'll have a big peak. So it's very dependent on the end of life. And timber don't have a module D either, because you can't recycle them. So there is a lot of controversy over the carbon accounting methods for timber products, for when and how the stored carbon can actually be considered, which can in turn lead to misleading claims on the carbon emissions in certain infrastructure assets, with various jurisdictions having different rules and assumptions. So back to our investigation of looking at how potential carbon reductions for the proposed CTH system can be achieved. So first off, we'll look at the typical cumulative carbon profile of the steel solution, and then we'll go into our results of our theoretical solution for the CTH with different end-of-life scenarios for the timber. So the cumulative carbon profile of the steel solution is stable once it's constructed, and we've assumed that no maintenance takes place. And then at the end of life, because of steel being able to have a high recyclability, the module D actually provides a significant carbon benefit, where we can see this reduction here past the 100-year mark. So when we introduce the CTH, we can see that we've got the 25-year harvesting cycle here, which we saw before, and then following this the carbon profile stabilizes. However, at the end of life, due to the EN standard 16,484, the carbon is actually assumed to leave the system boundary to ensure that future products don't claim this sequestered carbon as well, so we prevent double counting. So as you can see from the EPD, we've got the stored carbon as minus 804, and then at the end of life, all of this carbon gets released in theory to prevent that double counting. So consequently, that sequestered carbon becomes negligible, and we then get that drop due to those main steel girders there in the module D. So these findings are pretty controversial, as in reality, if you recycled or reused the timber product, the carbon would remain stored within the material and not released into the atmosphere. However, we've just followed the data set out in the EPD to show how it's actually represented through the data. So the EN standards have set out that these principles to prevent double counting of sequestered carbon. However, if we create a reuse case for timber and it's promoted and established, these products could have their own EPDs, which would include a carbon release at the end of their life instead of in the first use case. And similar EPDs are available for reuse of steel products, which show significant carbon saving compared to an EPD of virgin steel and possibly even recycled steel. So furthermore, the approach outlined in the I-D states that carbon storage can only be considered if there is certainty of the end-of-life process, so that it does consist of reuse and recycle. And this is completely different to that guidance that's set out in the EN standards, and hence how it's outlined in current EPDs. And this data is what is often driving decisions. So in the next scenario, we've got the glulam cross girders with the end of life scenario of being sent to landfill. So this carries a similar profile, where we've got that carbon reduction for the first 25 years. However, at the end of life, we can see a huge reduction here. So this is because in the EN standards, the landfill gas is assumed to be combusted for energy recovery. And this resulting electricity receives a credit for offsetting average electricity from the Australian grid. So this can be seen in the EPD, where we can see that the carbon sequestered on the left, minus 804, and then we've got the 2.98 on the landfill. So basically, it's assumed that all of the gases that are within the in the landfill, within that stored carbon product, are actually kept in there. So in addition to this study, they also found that when wood is put into landfill, the conditions allow for minimal degradation of the wood to occur. Hence, minimal carbon, actually around 4 to 6%, is actually released from the timber product into the atmosphere once it's into landfill. So consequently, by using either one of these assumptions at the end of life, the carbon that was sequestered within that 25-year period here is assumed to be trapped and not released, proving to have significant carbon benefits in comparison to the all-steel scenario. So these results are obviously extremely surprising, but actually understandable when you think that the majority of the timber sequestered carbon would be stored in landfill and not released into the atmosphere. However, with this showing as the lowest carbon solution, this is actually misleading. Obviously, sending timber to landfill is not the most effective scenario, and we need to promote material circularity and not encourage sending materials to landfill. And this shows how the data that we have at the moment might be leading us to make ineffective decisions. However, if we can take this key principle that sending timber to landfill is the lowest carbon option because it's enabling the carbon to be stored and not released back into the atmosphere, how can we use this concept to innovate? How can we ensure that the carbon is stored and trapped inside the timber without having to send it to landfill? So in addition, we've evaluated how using low carbon steel impacts the results. So the dotted lines from the original Liberty Steel EPD, and we've compared that to a lower carbon alternative of the Exla plate. So from this, we found that we can achieve further carbon benefits with the CTH solution. And we've also had a look, so replacing it with the timber cross girders, we can achieve even bigger reductions. So taking into account module A to C, we found that we can achieve up to 40% reduction when combining low carbon steel with glulam cross girders. And when evaluating module A to D, we can achieve 42% carbon reduction when combining the traditional steel with the glulam cross girders. So these results differ slightly with that module D component because the lower carbon steel actually has a less significant module D than the traditional steel. So that's where we've got these increases here, which might be a bit confusing. However, obviously, where we're getting these big reductions is where we're sending the timber to landfill. And this obviously isn't okay to just assume that we can do this. So this isn't the right solution. However, if we think about what we've learned here, the success story of carbon benefits related to timber are directly correlated with its end-of-life scenario. So can we develop timber products to ensure the stored carbon is locked in to the timber? And this is where the innovation is needed. So in summary, our CTH solution can give a carbon reduction of 42%. However, to realize these carbon savings, we need to design timber structural members in a way that they can be reused or recycled, or that the carbon can be secured in the timber product without sending that to landfill. So through this investigation, we found that there are limitations in current carbon accounting practices, such as the assumptions related to reuse and recycling of timber and sending timber to landfill. And the standards and guidance need to promote material circularity and incentivize designing timber structural elements for reuse. And lastly, we need to maximize the benefits of each construction material and use the right material for the job, whether it's steel's high strength to weight ratio or timber's carbon sequestration ability. So as the next steps, we are continuing to develop the technical design aspects of the composite timber hybrid concept. And the next part of this will be presented at the upcoming New Zealand Transport Agency Bridge and Geotechnical Conference in July. So I'll be really happy to share the presentation with everyone who's attended today and who's interested, followed by actually designing and building such a bridge. So if you are interested or you would like to find out more information, please feel free to contact us. Thank you for listening. Any questions?
Awesome. Thank you, Larry. So just a quick reminder, everyone, any questions, please put it in the question box. And like Larry said, everything will be given out for you in the handout later. This recording will also be on YouTube. So your YouTube star now, Larry. So just for questions. So I do have one question. You mentioned earlier about we use the iStract LCA method. Now, can you just give us a bit of a commentary about if you use the iStract tree method plus one used in New Zealand versus one used in Canada, for example, or Australia, will you end up with the same results as in the numbers, or will it be, or not? I mean, any comment on that?
Yep. Yeah, so the I-D method is really detailed and outlined in the PDF that you can get off their website. So it's you'd end up with the same results, but the controversial thing is you have to actually go against the data that's in the EPDs because of the EN standards of how they outline what we should assume for reuse and recycle, where you assume all of that carbon gets released. However, in the I-D method, obviously rightly so, that if you are reusing that timber, then you can assume that you've got that that carbon stored within your infrastructure asset. So they would be different results from, international standards, which is quite interesting.
Yeah. So I guess one of the challenges is when people do these is to use the same process every time they do another example. Otherwise, you'll have comparing different things. Okay, we do have a couple of questions. Is there a plus carbon in that study to account for the loss of timber's carbon storage benefits, which are lost when it's cut down for reuse?
So the harvesting rate, so again, the approach was taken from the I-D timber and carbon sequestration report, I think it's called, where basically, obviously, we've assumed that we've got sustainably sourced timber. So with that harvesting rate, the reason why you can only take that after 25 years is because you chop a tree down, you use that, and then they replant a tree, and that tree has then grown and sequestered the carbon that you've kind of taken from that. So that's how you're accounting from it. Whereas if you had unsustainable timber where you hadn't replaced the tree, then obviously you can't have any of that carbon stored within your calculation.
Yeah, so it's very dependent on the calculation method and the EPDs and so forth, which was some of the things you did mention earlier. Okay, have you considered the recent WRI report, which I don't know what that is, so whoever sent that, can you please just let us know where that is from? That finds that biogenic carbon sequestration figures are widely overestimated due to land use change, and less than 20% of timber material felled making their way into long-lived products. Again, isn't this an EPD issue or EPD thing?
Yeah, it should be covered within the EPDs, but I think that's what we did find when we were looking into this is that, there's a lot of research out there of how much timber actually gets used. But again, we can only use the data that we get given within an EPD, so it is a data-driven system. So, yeah.
Cool. So hopefully one day those people who prepared the EPDs would have read that report and treat it accordingly. Okay, here we have an interesting one. I may answer this one. How will long-term effects of less carbon in the atmosphere affect the planet, since carbon is vital to life on Earth as a building block? I think I have an answer to that. So this is one of the things I've been struggling with personally for the past few years and through my own journey through decarbonization. And we still have different views about carbon and how we account for it or what its effect. So my understanding now is, yes, the more increase in carbon in the environment results in a greener Earth, more trees and so forth. However, it also means that at some point we're going to lose the ice caps, for example. So 10, 20, I think over 20 years ago, the amount of carbon in the air was around 375 parts per million, which is what we're used to. But as of a couple of weeks ago, it's now 425. So yes, carbon is important for life, but we're actually at the moment at the high rates of carbon, where my understanding is if we hit 450 parts per million, we would lose the ice caps, which in turn results in higher sea level rise and so forth. So what we're trying to do is trying to capture and make better use of the materials that we have, which is why we're advocating for the reuse of timber, extending the life of materials. And personally, I would like to see a greater design life of buildings and bridges. So why do we design a bridge for 100 years? We can design it for 200 years, for example. And it's all about efficiency of design. So we're not advocating one material over another. We're advocating for all materials, and you just use our smarts to make them last as long as possible, while reducing the amount of carbon being released in the air. So it's a great, again, like Lowri said, it's a great opportunity for innovation, for something new. Any other questions? Oops, here we go. Okay, is there an LCA approach that factors the time values of emissions? Oh, okay. Example, 100 tons CO2 equivalent today is worse than the same 100 tons CO2 equivalent at end of life after 50 years. Example, timber benefit is upfront, steel is end of life. What do you
Yeah,
think?
that's a really good question, actually. And I think that's where, because the cumulative carbon profiles aren't usually done when we do a carbon assessment, but I think doing it that way actually does show, when the carbon is actually going to be released and when it's most beneficial to do that. And I think obviously nobody knows what situation with carbon we're going to be in 100 years, so it's quite a difficult question to answer. You'd hope that we would be in a lot better place and that you could afford to produce a bit more carbon. But I think, yeah, I think it's a really good question. And I think it's a lot of people would have different opinions on when is the best time to release
Yeah,
carbon. But overall, if you can get the lowest carbon approach, then that's greatly beneficial.
yeah. So my understanding, again, if you look at timber by itself, which does give you, even with it, the 25-year harvest period, as we showed, does give you that reduction now or within the next 25 years. But the challenge, my understanding from the industry, especially here in New Zealand, and I appreciate every country's got its own different capabilities. We are not, yes, we do have the trees, and yes, we can grow the trees, and there's a different paper I gave about what happened to those trees. But the challenge is, do we have enough manufacturing capabilities to transform everything into timber, for example? And the answer that I was told from the industry itself was no. Hence, what we're proposing here is, again, using the benefits of each material, whether it's steel, timber, or concrete, maximize their potential by combining them together into hybrid systems. We believe, as we showed, that gives you a lower in-service carbon and with a greater potential for reduction at the end of life. But hey, I don't know what happens in 100 years. I won't be here. But we're doing the best we can with the information that we have and the capabilities that we have. I think there's a follow-up. Okay, have you considered minimizing steel emissions before recycling them, as they mostly, well, the questions are coming now. Before recycling them, as they mostly release when they're out cut into sections, and could these likely release more emissions as compared to the initial production too, because they're cut and resized? I think this is a question from a fabricator, or a very specific question. Before recycling. So my understanding now is there are two processes of steel making. We have, well, there's potentially three, but we have the blast furnace and we have the electric arc furnace. And blast furnace use virgin steel and electric arc use recycled steel, which is why we are able to get the lower carbon steel, potentially up to a sixth of what the benchmark dirty steel is achieving. So you can get new steel from arc furnace, which is very low carbon. And we just had one example, but that'd be a great study to look into the different possibility. The issue, as I mentioned earlier with the manufacturing, is we don't recycle enough steel to turn everything into low carbon steel. So there will be potential for improvements over the years, which is where the new Swedish hybrid method and all, hybrid method is where they're using hydrogen. And so this is now all the new sci-fi new stuff. But again, that's why we said we don't expect that type of manufacturing to be available for till 2030, probably by 2050. So yes, so that's the question relating to manufacturing low carbon steel. And yes, when we do fabricate, there will be carbon released. But again, that's probably a relatively small compared to the actual manufacturing itself compared to cutting steel. But it's all about, that's where the innovation, we really want people to start innovating, thinking, and a lot of stuff is happening now. They're even talking about reusing concrete a couple of weeks ago, where they smash it and they reuse it back into cement, which combined with the heat generated by steel making. I think I posted that on my LinkedIn a few weeks ago. So again, innovation is happening, and things are getting better. Okay, oh, there are two more questions. Yep, this is the last one now. What is the reality of acquiring enough sustainably sourced timber? I have a story about that one. For the infrastructure needed in growing population, human environment, I'm assuming sustainability source is a lower available resource. Sustainably sourced is a lower available resource. Do you agree with that, Larry? When you have a
I
sustainably
think it will
sourced timber,
completely, yeah, it'll completely depend where you are. Obviously, the situation in New Zealand will be completely different to other places and how much land use you've got available to use. But yeah, in
yeah,
New Zealand, I don't think anybody would use unsustainably sourced timber because you're better off just not
yep,
using it, is my understanding.
yep. So, but I do agree. Um, Again, we can grow as many trees as we want, but if the growing trees start affecting our food source or our built environment or whatever, that's a question for each country to consider. But yeah, and I'm not a fan of cutting down old growth. I think those forests should remain because they are greatest carbon sink. But anyway, that's it for today. Hopefully you all enjoyed it. Again, like Larry said, we are giving the second part of this presentation where we'll be focusing more on the design aspects of the composite timber hybrids solution that we've developed in a couple of months. And if there is enough interest, we could possibly do another video like this, or we could just share the presentation depending on the level of interest. Just email us. Our details are here. And thank you all for coming.
Thank you.